chat. I am the host now. Wow. Come on. Okay. Hello, everyone. Let's see. We're going to do a couple things today to end the week. Bringing up my camera controls, which I can't open until I've started my Zoom session. Okay. Let's see. Boom. Maybe something like that for now. Okay. I'll go to the other camera. Okay, so today is going to be the start of kind of wrapping up talking about gravity and orbits. Of course, this week's homework is all about gravity and orbits, and starting to talk about, starting to talk about chapter 14, oscillatory motion. Let me take a glance here at this course schedule, remind myself how many days we're going to spend on oscillatory motion. Kind of 3 days, so Friday, today, Monday, Wednesday, we're going to talk about something oscillating, maybe a mass on a spring or a pendulum. Those are going to be our two kind of most common go-to examples, but there are many other examples. Going to touch on at least a couple more examples of what we call simple harmonic motion over those days. And then by this time next week, we will, so next week's homework is almost all from chapter 14. Let me remind myself. It is almost all from chapter 14. 2 questions from chapter 13 about gravity. I was just kind of glancing at the course schedule there. So that's kind of the next week. And then from that point on, we're going to talk about rotational dynamics, rotational mechanics. It's a pretty good way to end the semester. Getting ahead of myself a little bit, but it's a pretty good way to end the semester because it gives us a chance to revisit a number of topics from earlier in the semester, but now we're going to talk about them in their rotational version. So there's velocity and there's angular velocity. So we get to kind of revisit we get to revisit kind of velocity issues when going over rotational motion. So it's a good way to, it's a very important topic in and of itself, rotational motion and torque, like yesterday's lab, for example, but also it gives us a chance to, as the course is kind of nearing the end in the second half of April and the beginning of May, it gives us a chance to kind of naturally do both a new topic and revisit previous topics, motion topics, Newton's laws and free body diagrams, lots of topics, energy, work, kinetic energy. Today, we're going to do 3 things. I'm going to start by doing a fair amount of time working through the algebra of a practice question. This is what was, some version of this is what was going to be the handout homework question for this week, and I kind of decided that between last week being Good Friday and us not having that day of class, and maybe a couple other things, that I would just kind of do these problems that I had in mind with you guys, or do most of the parts with you guys. So there is no handout homework question for this week. It's just, I think it's 2 questions from chapter 8 and the rest from chapter 13, maybe a total of 8 problems. And I think I just recently in the last hour or so put up the assignment link for that homework set. I think I initially put it up as due at 6 a.m. this morning, which was a mistake by me. It's now entered as an assignment that's supposed to be due by 6 p.m. on April 17th, tonight. Okay. Let me show you guys some stuff. I'm kind of expecting that when I go to share my screen the first time or two, that maybe my video is going to have issues and kind of start to get quite glitchy. We'll see. That's my expectation. And then I'll be kind of working up here on the board a little bit. So let me show you a problem, a file with a problem with many parts that was just recently put up on Moodle. I might adjust it a little bit and repost it with maybe 1 or 2 more additional questions asked, but the key information will be already shown in these parts. I think there's like about 9 or 10 parts. About orbits, about orbital motion. In this case, we're not going to be orbiting the sun, we're going to be orbiting the Earth, but that's not it. Well, I'll show you page here. Yeah, down at the bottom. Not quite far enough. Here we go. Right here, orbital motion practice problem. And it looks a bit like, that's not it, that's the other class. Yeah, that's it. Orbital motion practice problem. Okay. And I'll be showing you maybe some Desmos file, a Desmos file to go with this. I probably will include that link on this page. That's another reason I'm probably going to update what's there. But if you want to kind of read the basic version that you see right now, you can already see that on Moodle. Okay. I included the same information as at the top of another sheet. I don't think we're going to really need this gravitational field near Earth number, but definitely mass of Earth, radius of Earth, gravitational constant. In particular, capital G times capital M as a product is going to show up over and over and over again in pretty much every key scenario, every key equation or result. So here is the scenario. A 4,000 kilogram satellite is in an initial circular orbit around the Earth with a radius of 8,000 kilometers. We want to move this satellite out to a new circular orbit with a radius of 11,000 kilometers. And the key question is going to be, how will we get between these two orbits? It's not very difficult to get into a circular orbit, which we're going to kind of analyze in the first 5 parts here very quickly. 2 circular orbits, the small and the large. Pretty easy. We will start by working out some details for the 2 circular orbits, but then what we really want to focus on, it's kind of down here, excuse me, a little lower. To transition from the inner circular orbit to the outer circular orbit, we will need to use an elliptical orbit to link the 2. Do that, whoop, like that. So up above in A through E, we're talking about the circular orbits. I think I did a lot of subscript C's for circular. So what's the velocity of the circular orbit? And maybe think of this as number 1 and number 2. Circular orbit 1, circular orbit 2. And for the ellipse, we want the ellipse to touch the inner circular orbit at one point on the ellipse. And we want the ellipse to touch the outer circular orbit at the farthest point on the ellipse, and those are called perigee and apogee. If you're orbiting the sun, it's perihelion and aphelion. So 8,000 kilometers circular orbit is going to be the nearest approach of the ellipse. 11,000 kilometers circular orbit is going to be the furthest approach or furthest outward point from the Earth for the elliptical orbit. And then we're revisiting pretty much all these issues from A through E in F through I. Speed, kinetic energy, potential energy, total energy. So D is probably the easiest part on here. You just add up kinetic plus potential. So if you fill in B and C, it takes very little time to fill in D. And then as a separate issue, what is the period of the satellite's orbit? And down below here, it would say, what's the speed at each point? So at perigee and apogee, kinetic energy, potential energy. For total energy and for period, where am I? Okay. For total energy and for period of the elliptical orbit, it does not distinguish between at what point, because the total energy doesn't change as you go around any orbit. So the total energy, isn't one value at perigee and another at apogee. It's just the whole thing. And period refers to the entire orbit. So that's just a single number. So actually, I didn't mean to really have 2 blanks here. I just meant to have 1 blank. And I think I'll change that. And I'll just kind of do something like that. That's what I meant that to look like. Now, I actually do have 2 energy blanks here, but the expectation is that these are supposed to be the same. These are supposed to be the same. Maybe I'll even kind of write that in here. So those should be the same, because energy doesn't change as you go around in orbit. Oh boy, okay. I'm trying to get that a little smaller. All right, let's go with that. So those are expected to be the same. Okay, the easy part of this question, honestly, that you should have really little trouble doing, and there's many homework questions, I think, for this week and maybe the 2 on next week's chapter 13 questions. The easy questions are the circular orbits. If you're given one piece of information about a circular orbit, let's say the radius, you should be able to find everything else about the circular orbit, honestly, quite quickly. It doesn't mention acceleration or force on this list, but we could add those to the list. So if you tell me the acceleration of the object in the circular orbit, I can find all this stuff: radius, velocity, kinetic, any kind of energy, and period. Most commonly, what we tend to know most often as a starting point is we either know the period or the radius. If I had my choice, and you could tell me, Professor Feig, you get to know one piece of information about a circular orbit. Well, what one piece of information do you want? I would probably choose to know the radius. And to be clear, you only need to know one piece of information if you know the object that you're orbiting. So if you know information like capital M of the object being orbited, then you only need one piece of information. If there was a different question where it said something like a moon, let's see, if it said something like a planet is orbiting a distant star, but I wasn't given information about the planet or the star, then I would need to know two pieces of information. I would either need to know radius and force, maybe radius and period, or I could be told radius and mass of the star being orbited. So if you know what you're orbiting, one piece is enough. So let's just go through this. I'm just going to kind of work out the equations, and then we'll pump in the numbers. And remember, I'm going to kind of use really millions of meters as my unit of distance. This is 8,000 kilometers in millions of kilometers, or mega meters. That'd be 8 times 10 to the 6th meters, 11 times 10 to the 6 meters. And just for comparison, what is the radius of the Earth? I don't think we're going to use this number in the calculations, but for comparison, the radius of the Earth is around a little over 6 million meters, or 6,000 kilometers. And these orbits are obviously larger than that. 8,000 is the inner one, and that's bigger than the radius of the Earth by a fair amount. Here is a little visual representation of the orbits. You guys can see that. So that's to scale. The Earth is green. I might at some points turn off the Earth or just make it look like the dot just for visuals. The Earth is that big to scale. And you can see, I think I put RE is 6.37. So what's the unit of length? Kind of, if you see an R slider, the unit of length is thousands of kilometers. If you want to know how big the Earth is, it's that big. If you just want to kind of represent the object being orbited as a dot, there's the center point. And if I go up here, I can kind of adjust these guys. How big do you want the inner orbit to be? How big do you want the other orbit to be? I guess you could have them switch. So I'm going to call these R1, the orbit you start in, and R2, the orbit you end up in. And you could move these around later on after we get some values on the screen. And here we go. What are some things that we should be able to calculate pretty easily? All this stuff. I know the mass of the Earth, I know capital G, and you give me a radius, I can calculate all this stuff. So I'm going to go through these pretty quickly. Velocity, period, and then all the energy types. So I think I'm going to take it off the share and kind of do this on the board. It's not too bad. of algebra here. And I'm looking for one thing so I can zoom you guys in a bit closer. I think I'll go to about there. Okay, where's my markers? Okay, here's how I would do it. Now, Kepler's third law will answer some of this for you, but here's how I would do it. And along the way, I'm going to derive Kepler's third law in the case of circular orbits. It is important to remember that Kepler's third law applies even if the orbit is not circular. So here we go. If you give me radius, my first thought is I can get force of gravity. Okay, we know all this stuff. We know mass of the Earth. We were given a mass for the satellite. The least important number that you're provided is the mass of the satellite, which is 4,000 kilograms, I believe. But that is the number we're going to use. But that number has very little effect on most of the key information. It has no effect on the radiuses, the times, or the speeds, or the shape of the orbits. It will affect kinetic energy is proportional to mass, potential energy, and total energy and force are proportional to mass. So here's my thought. This is MA. And if you want to call that mg, you could call it mg. I'm going to call it A acceleration. So what's the acceleration? Obviously, just cancel off the m's there. So I'm just going to say force of gravity divided by mass is acceleration. So let's just calculate the acceleration for both orbits, or we could if we wanted to. There it is. We're given two r values. What about speed and velocity? Velocity is distance for one orbit over time for one orbit. And maybe one more thing, centripetal acceleration. So for a circular orbit, this is going to be true for circular orbits. Obviously, I use the idea of a circle because what's the distance around a circle? Circumference 2 pi r. And then for circular orbits, acceleration is centripetal acceleration v squared over r. So this is true. This is always true. I don't care what kind of shape path you're going in. If your distance r from the center of the Earth, this is your acceleration due to gravity. And that would be the only acceleration that'd be relevant, would be due to gravity. So if I set these two guys equal, I could solve for a relationship between, here I have a relationship between A and R. If I set these guys equal, I can make that a relationship between V and R. And then if I use the middle fact, then I can get a relationship between T and R. Let's just do that really quick. So acceleration on the one hand is Fg over little m, and on the other hand, it's V squared over R. So what if you solve for V? Cancel off one factor of R, you get gm over R, and that's V squared, and you take a square root. Not too bad, right? How is acceleration related to radius? Acceleration is 1 over r squared compared to radius because force is 1 over r squared in Newton's law of gravity. How is velocity related to radius? 1 over the square root of r. So if you think about what that means, as you go to larger radius circles, you're moving at a slower speed. Why does it take Mars longer to orbit the Earth? Sorry, why does it take Mars longer to orbit the sun than the Earth? Reason 1, it's going around a bigger circle. Reason 2, it's going around that circle at a lower speed. So it takes quite a bit longer for Mars to orbit than Earth. And we can look up Mars, I think it's around 3 years, as opposed to, of course, Earth being 1 year. So I'm just going to put that one there for safekeeping, and then we're going to use that to fill in the velocities. Right now, you can just do g times mass of Earth over 8,000 kilometers, or put 8,000 kilometers into meters, take a square root, and you'd have the first speed, and then replace 8,000 with 11,000, you'll have the next speed. I'm going to go one more step. What if I set velocity equal to 2 pi? The a value is for a circle. It's the radius. So that is a very quick way to derive Kepler's third law for circular orbits. And what were the starting points of that calculation? Force equals mass times acceleration, Newton's law of motion. Capital F equals capital G m over r squared, Newton's law of gravity. And then doing some calculus, which we did a long time ago, to figure out that for circular paths, acceleration is v squared over r, which follows from, like, definition of velocity and acceleration. So you take kinematics to get centripetal acceleration, Newton's second law, F equals ma, to describe any kind of motion, Newton's law of gravity, capital G m1 m2 over r squared, to understand the pull between Earth and satellite, and you're going to come up with this relationship for any circular path. Where did the 4 pi squared come from? It came from 2 pi describing a circumference, something about a full circle, maybe not too surprisingly, involving 2 pi. But then along the way, when the t got squared, the 2 pi got squared. So you get 4 pi squared. Or you could take the square root of this and write it as the square root. This is the way it's very commonly written. T to the second power is proportional to r to the third power. If you want to take a square root, go ahead and take a square root. And then this would become, take a square root of everything, or I guess you could put the 2 pi out front, and maybe you could write it like this if you wanted to. 2 pi r to the third power over capital G, capital M, square root. That's just taking the square root of the previous formula. Okay, so in summary, what have we got here? Here's a couple quick facts for circular orbits. A equals capital G, capital M over r squared for anything. V, capital G, capital M over r square root. And I'm just going to say T 2 pi r to the third power over G M square root. Hopefully it's on screen. And we can just pop these numbers in. And I'm really focusing on the r's. Bigger orbits have lower accelerations because they're further from the Earth. Bigger orbits move at slower speeds. Bigger orbits take a lot longer time. Okay, let's plug in some of these numbers for the circular orbits given in that handout. Share screen. Share screen. I'm going to go up here and try to get to this tab. Nope, not that tab, that tab. And this time I'm going to go to the scientific calculator option for Desmos, which is also pretty helpful. So V and T are on the list of things I'm going to calculate. I'm going to do V for both orbits. Square root 6.67 times 10 to the minus 11 times 5. I'm going to do velocity first. 5.98 times 10 to the 24 kilograms. And then the first radius is 8,000 times 10 to the third, 8,000 kilometers. So that's going to be 8 times 10 to the sixth. And there's the velocity for the smaller orbit. And I could do the speed a couple different ways. I'm going to do it 2 ways. I'm just going to do time is okay. So there you go. And that should agree with just doing this directly, but I'm not going to do that directly. Just trust me, or double check. Don't trust me that Kepler's third law would give us this same period. So what did I do here? Distance for one orbit divided by speed is time for one orbit, and this is in seconds. So you're orbiting at about 7,061 meters per second, and it'll take you 7,119 seconds to orbit. How long is 7,119 seconds, just for kind of context? What if I did answer divided by 60? Oh, so that'd be 118 minutes. Okay, and if I just take all these, and I'm going to write these answers in here a little bit. 7,061 meters per second, 7,119. 7,061 meters per second. And then I think we got a period down here of, let me remind myself, 7,119 seconds. I'm going to say 119 minutes. Okay. And then let's just go here and switch over to the new ones. I want to get the new numbers, but all I'm going to do is replace the 8s with 11s, the 1 8 with 11, and then this 1 8 with 11. So there we go. Bigger orbit, you're moving slower. It takes you more seconds and more minutes. 191 minutes, 6,022 meters per second. Okay. 6,022. 6,022, and how many minutes was it? 160, 191. Okay. All right. Now we can very quickly get these other guys. Another number you might want to list is what is the gravitational acceleration? That's almost the same as force, right? If you take this and multiply by a little m, then you get force. Okay, can you guys find the kinetic energy and pop those in? We know the mass of the satellite is 4,000 kilograms. Haven't used that number yet, but now it's going to matter. Right there it says 4,000 kilograms. So 1/2 mv squared. We got v, we got m. Let's just do 1/2 mv squared and get kinetic energies. And how do we get potential energy? Potential energy directly relates to radius. What is force, capital G, like this, And stop share. So here we go. Force. This was really the starting point of all this. And then what about kinetic energy? Well, kinetic energy, of course, is just 1/2 mv squared. Can anyone tell me what you're going to get if you take this formula and you square it and you multiply by 1/2? And when I say 1/2 m, I mean little m. So square this, gets rid of the square root, and then multiply by 1/2 little m. So kinetic energy for a circular orbit is GMM over 2 little r, right? We just went from here to here very easily. Here to here is very easy. Here to here is very easy. So okay, here it is. Yeah, what I need, left it around the corner. Oh, what's going on? All right, so I'm pulling up on another device my key results, and we're going to derive most of them. Okay. Let's talk about the orbits that aren't circular. Here's a pretty good visualization, a starting point visualization. Can you guys see that pretty well? I think I might move this way a little bit. That gives me more of the screen that I can get to. Okay. Let's say you're going around the inner circle and you're like, you know what? I really want to move out to this other orbit. The new orbit will be bigger, slower, and take longer, but I need to be in that orbit for some reason. How do you get from here to here? You don't, I mean, you could. Here's one way you could do it, which isn't a great way to do it. It would work. You're moving around here. You fire your boosters, so you stop going up because you're zipping around at a pretty high speed. You fire your boosters, so you stop going up, and then you fire your boosters again, so you start going, you know, from red to yellow. And then when you get to yellow, you fire your boosters again to get you into the right speed to follow the yellow path. So you stop your orbital motion, you head outward, and then you kind of restart your orbital motion. And that would be like to take the straight line path. And you could do it, but it would cost you a lot of fuel if you were a rocket or a satellite or a space shuttle or anything like that. It would cost you a lot of fuel. And what would be probably more efficient use of your fuel to get from red to orange is to do this. Let's follow right here. Should I do it like that, or like that, like that? Let's follow this path. Can you see that there? So I'm going around the red one, and when I get to right here, I'm going to follow this path out to the yellow one, and then I'll follow the yellow one. What is the purple path? It's an ellipse. It's just I'm only going to follow half the ellipse. So if you can see that there, that's kind of what we're going to do. I'm going to take the green one off just because it's just more to look at, and it doesn't really change anything very much. So we want to use the purple elliptical path to link the inner and outer circular orbits. Of course, we're only going to follow half of the purple, but there's kind of the whole thing shown. Where is the purple path centered? It is not centered on the Earth because what is Kepler's first law of planetary motion? The thing being orbited resides at one focal point. So here is the actual center of the purple path, but there's the other focal point. Maybe I'll just take off some things for us to view. So we now need to talk about this path. We're orbiting the green dot, but this is the closest approach, perigee, and this is the furthest approach, apogee, green to here. And let's just put some things back on here. What if you wanted to get out to something like this? from something like this, like that would maybe be a more extreme version of it, right? From a very small circle of relatively small circle of radius 4 out to a circle, let's say, of radius around 12. This is why I wanted to take the Earth off of here, because can you orbit the Earth at radius 4,000 kilometers? No, because that's actually down inside the Earth, but you can represent it as a nice elliptical path. Let's see. So there we really see the elliptical stuff occurring, where the center of the ellipse is the purple dot. The Earth is at one focus. The other focus is empty, but I'm just representing it visually. So I think I'm going to keep these guys drawn about like this. We're going to stick with the numbers 8,000 and 11,000, but just for visuals, I think just to have a more obvious kind of difference between the inner and the outer, maybe we'll kind of view it like this. So how do I get into this elliptical path? I want to find the speed of the elliptical path at red, and I want to find the speed of the elliptical path at meeting up with yellow or orange. How am I going to do that? I need to think about a little more deeply. The math is going to be more algebra than this easy algebra, just multiply, divide, square root for circular orbits. This is what it's going to look like here. Okay. I'm going to focus on two quantities that are conserved as the object follows the elliptical path. I'm going to call this right here R1, and I'm going to call this V1E. Am I on the screen, off the screen? I'm on the screen. And then over here, I'm going to call this, this is the Earth. So that is radius 2. And then this is going to be speed 2. And speed 1 is faster. So I want to kind of show it a bit like this. And I'm not calling these V2C, because V2C for me would represent what speed you'd be going at right here to be in that large circular orbit, or V1C circular. I'm going to call these V1E and V2E. Do we know anything about how these numbers relate to these numbers? Because I want to find the V's, and I know both R's. And of course, I also know what I'm orbiting. I'm orbiting an object with a mass of 5.98 times 10 to the 24 kilograms. How do you get from here to here? Or what do we know about this path? Two things. Energy is conserved. Can we write that as an equation? What's my energy here? Kinetic plus potential. What's my energy there? Kinetic plus potential. That's going to relate V for kinetic and R for potential. So here's my equation. I think I have enough room. I'm going to give myself a little more room. So energy is conserved. I'm just going to write energy. 1/2 m V1E squared minus capital G, capital M, little m, R1. This is the kinetic plus the potential energy at position 1, and I'm just going to set it equal to the exact same statement, replacing the 1s with 2s. That should be the same as 1/2 little m V2E squared minus capital G, capital M, little m over R2. And what's my goal? My goal is to solve for the velocities. So I'm trying to eventually find the velocities, V1E and V2E. I know all the black stuff. Can you solve this equation for the velocities? No, we need a second equation if we're going to solve for two variables. Energy is conserved. What happens to the speed as you go from here to here? The radius goes up, the speed goes down, but this combination is energy, and that does not change. What else? What's another fact I know about there and there that I can use to get a second equation? What does Kepler's second law say? And Kepler's second law. What's going on? That's not the right class. There's your class. Kepler's laws. What's the second law say? Planets move faster when they are closer to the sun in their orbits and slower when they are further away. You can express it in terms of areas. I'm going to go down to the final bullet point here on this handout. Oh, gosh. On this handout about Kepler's second law. Kepler's second law is equivalent to the statement that the planet's angular momentum is conserved. Angular momentum is discussed in chapter 12, but we're going to use it right now. Do you guys remember what I said on Wednesday about the formula for angular momentum? It's basically radius times perpendicular velocity. It's actually officially little m, mass times radius times perpendicular velocity, but the little m's are going to cancel out. So angular momentum is a much shorter formula. And Kepler's second law is equivalent to saying the angular momentum doesn't change. We'll explain why that's true when we do chapter 12. But this is a very simple equation. Mass times how much of this velocity is perpendicular to R1. At apogee, it's all perpendicular. And at perigee, it's all perpendicular. So I don't have to do any weird angular stuff. At this point in red, it's easy to do angular momentum. And at this point in red, it's easy. Everywhere else, it's a little more complicated. M times V times R. And then this should just be the same. At the close-up point, at closest approach, R is small, V is big. And at the furthest approach, R is big, V is small. Okay. Now we've got two equations and two unknowns. Do you guys think you could do some algebra and solve this pair of equations to get the red stuff? To get either the red or the blue, green. Maybe I'll do this in green. Could you do that? It wouldn't be too bad. Really quickly, what would a pretty good way to do the algebra be? What would a suggestion be? If you had to solve and get red, what would you do? You could solve this very quickly, let's say for green, and substitute that. You know, solve for red in angular momentum. I can't quite read it. It's half on my screen, half off my screen. Solve for red in angular momentum and substitute it. So the way Darren did it, he would get rid of red and find green first. Great. You know, either way. By the way, what happens with the little m's? Everything is proportional to little m. So it cancels out of both these equations. So as a first step, I think I might cancel the little m's and then maybe multiply this whole equation by 2 so I don't have the 1/2. You know, you could do something like that pretty quickly and you'd be starting to get to a pretty good spot. Put a little 2 up, big 2 up here, put a big 2 up here, get rid of this, get rid of this, get rid of this. Maybe I'll divide by R1, you know, V1E. Okay, V1E is this, and then I'll just substitute that in there. Just going to move this over a little bit. V1E squared. You know, it wouldn't be too bad. And I'm going to tell you the results if you were to do that. If you were to do that, here's what you'll get. The formula for V1E will involve all the black information. Some numbers like a 2, capital G, capital M, and both radiuses. Because I need to know both radiuses to kind of understand the full ellipse. What do we call the full distance across an ellipse? Half the full distance is called A. So what's the A of this ellipse? R1 plus R2 equals 2A. So you'd want to find the semi-major axis, which is half the long axis. The long axis is always closest approach plus furthest approach. I think I messed that up, by the way, on Wednesday. I tried to do it for Mercury, and I forgot to divide by 2. So I was getting that I was adding closest and furthest, and I wasn't dividing by 2. So I was getting a number like 0.4 astronomical units when I was supposed to divide by 2 and it was when I was doing eccentricity. I was getting an eccentricity of like 0.4, and it was stating on Wikipedia that's around 0.2, and I was just flat out forgetting to divide by 2 because A is not the full distance, it's half the full distance, just mentioning that in passing. Here's the results for the V's. Of course, they're very similar formulas for V1 and V2, V1E and V2E. The only difference is where does R1 show up and where does R2 show up. I'm trying to look for it here. There we go. Okay. Now you can write this a couple different ways. I'm going to write it like this. V1E turns out to be GM, and then is there a 2? There's a 2. And then on top and on the bottom you have R1 plus R2. If you do the algebra, you get a little bit of common denominator stuff going on, and that appears. And then in the numerator, we have R2, and in the denominator, R1. And then guess what the formula is for V2E? Same thing, you just switch these two. So V2E is basically a repeat. Same for addition. Switch the numerator and denominator for the R ratio. 2GM, add them together. R1, R2. Okay, or just take this formula and everywhere you see a 1, switch it to a 2. Everywhere you see a 2, switch it to a 1. If you do that, I think I'm just going to calculate those 2 speeds and then put those into the Word file, and maybe we'll leave it at that point. Because if you can find the speeds and you know the radiuses, you can get kinetic energy, you can get potential energy, you can add it up, you can do it all quickly. So I'm just going to fill in not all these blanks, but the speed at both points, because if I could get the speed at both points, I'd be in pretty good shape. Now, these are not the answers. I'm just going to highlight these and paste them here to get me started, because they're going to be around the right speeds. But I want to see what this actually ends up being. It's going to be something a bit different. All right. And I'm just going to do this on Desmos calculator. And I think I'm just going to start with this. I'm going to grab that whole formula as a starting point. And I'm going to go clear all. Okay, so what should I do to get V1? I should do G capital M in the numerator, but I should also have a 2 times all this. And then down here, I should do 8,000. What happened? 8,000 plus 11,000. And then over here, I want to do times a rate times, I'm just trying to get this. No, I don't want to do that. I want to get a fraction right here. Okay, this is what I'm looking for. And what am I going to put on top? I'm going to put, for V1, I'm going to put 11,000 over 8,000. Basically, I'm just going to write 11 over 8 because the rest will cancel out, right? Maybe I'll write it out. 11,000 times 10 to the third. And this is going to be 8,000 times 10 to the third. Now, why does it not like my formula? Anybody know what's wrong with my formula? Can't see anything really wrong. I don't understand where the period is. I don't understand the way that, so I wasn't supposed to be using multiplication. Oh, didn't want a multiplication sign there. Okay, not a big deal. And then what's the only change from this to do the other speed? I just switched the 8 and the 11. So I'm just going to write those two numbers, 7598, 5526. 7598, 5526. 7598 and 6526. Is that what I said? 5526. 75, 98, 55, 26. Okay. So this is pretty good right here. And I just want to make a couple comments about how the four speeds compare to one another. Small circular orbit, transitioning to ellipse. At the other end of the ellipse, transitioning back to the second, transitioning back to a circular orbit. What do you notice about the progression or comparison of these speeds? To get from the circular orbit into the ellipse, what do you have to do to your speed? You got to increase your speed. So if you're in the circular orbit, what do you got to do if you're in control of the boosters on the rocket ship or the shuttle or the satellite? You got to fire the boosters to speed up from 7061 to 7598. If you do that, you'll stop following the inner circle and you'll start to drift outward on the ellipse. And then at the other end of the ellipse, how do you get out of the elliptical orbit? So you stop following the purple and you start following the yellow. You got to boost the rockets again to speed up from, while you took the ellipse, you drifted down from a high speed to a low speed, because as you move outward along the ellipse, you slow down. And then you need to boost the rockets a second time to go from the low speed to the required circular speed for the circular orbit. So what are we going to do with our rockets? We're actually going to be following the red, following the red, following the red. And when I get right here, fire the rockets and speed up. Then I turn my rockets off and I just drift. And as I drift, I slow down because that's how ellipses work. That's how elliptical orbits work. And when I get right here, I don't want to follow the dotted purple. So what do I do right here? I fire my rockets again. And once I fired my rockets to the appropriate final speed, I can turn my rockets off and then I just glide. And I glide around the big circle. The only time I have to fire my rockets is right now to get out of red to purple, and right now again to get out of purple to yellow. And you can very easily fill these in. These had better be the same for the total energy. The KEs are different because the speeds are different. The PEs are different because the radiuses are different. Total energy should agree. And that was how we use the fact that total energy agrees to get there. Another thing you could calculate would be angular momentum, which is MVR. MVR at the near point, MVR at the far point, those should also agree. So it's a little bit about kind of some more in-depth thought about circular orbits and trying to pull together force facts, energy facts, maybe even angular momentum facts. All right. That's what I want to get through. If people have questions about homework, you could definitely stick around and ask that. And I said we'd start to talk about oscillatory motion, but I think we'll actually start talking about oscillatory motion on Monday. Excuse me. It's a good topic. Springs and pendulums for the next week or so. If you guys have questions, you can stick around. Otherwise, it is 12:30. When do you think test will be in? Over the weekend. over the week. I have a lot of them. I mean, I have a good chunk of them. Sorry about that. It's dragged out. I'm not quite sure yet. I'd like to get you guys some feedback on the test other than just a score. Not quite sure how I'm going to do that, but I mean, definitely I can give you guys the scores, either in emails or Moodle. I'll get you your scores and maybe some feedback on which problems were stronger and weaker for you. It's coming over the weekend. Oh, yeah, sorry. Let's see here. Conrad, Daniel, Rockford, Zane, Jonah. Regan, Neil, Rockford, Jonah, just double checking. Anybody got a question? I think I'm going to close out the Zoom meeting. I don't hear somebody suggest something. Okay. Have a good weekend. Bye.